Section 8.3 is called the Integral and Comparison Test. So we're going to continue to work with series and ways to tell if they are convergent or divergent. So the integral test says, if I have a sequence that is a function of n, so it's the same concept we've seen before, I'm going to let the sequence, I'm going to take it and work with it as a function of n. Where that function is positive, ultimately decreasing, and continuous for x greater than or equal to 1. If you have those three conditions for this function, then if the integral from 1 to infinity of the function converges, you're guaranteed the series from 1 to infinity of that sequence also converges. Or if the integral from 1 to infinity of the function diverges, then the series from 1 to infinity also diverges. Now it says note the series need not start at 1, so notice that the bottom or the lower limit of each integral is 1. The series are starting at 1 and they are interested in these properties holding for x greater than or equal to 1. If you wanted your series to start at 2, you would have, of course, considered the integrals from 2 to infinity, and you'd be interested in x greater than or equal to 2, the function having these properties. Alright, so you can start it at any value you want to for the n, so 1, 2, 3, etc. Our first example says to determine if the series is convergent or divergent. I have a series going from 1 to infinity of 3n e to the negative n squared. If I'm interested in using the integral test on this series, well, in order to use it, there are three things that I need to check. First of all, I want to consider the sequence as a function. So the function that I'm looking at would be 3x e to the negative x squared. Everywhere there's an n, I've replaced it with an x. It's just function notation. This is the function that I'm interested in. I need to know, is this function positive, ultimately decreasing, and continuous? For x greater than or equal to, my summation starts at 1, so I am going to be interested in these properties for x greater than or equal to 1. Now, a couple different ways you could think about this. I think maybe one of the easier ways is to look at it graphically. So if I wanted to talk about this function, I have 3x e to the negative x squared. And I want to consider its graph. So I'll sketch it for us here. Notice it looks something like this. And notice that 1 is hitting somewhere in here, and x equals negative 1 is hitting somewhere in here. So these things are approaching the x-axis above. Here it's approaching the x-axis below. Now, things that I want to know, is this graph positive? Well, if you're looking at it as a whole, the answer is no. But remember, I'm only interested for x greater than or equal to 1. So from x 1 forward or 1 above, you'll notice that this graph is positive. Is this graph decreasing? Yes. And is this graph continuous? For x greater than or equal to 1, sure it is. So it meets the three conditions, which tells me I can use the integral test. Now, what the integral test says is that I want to consider the integral from sum starts at 1 up to infinity of the function. So the function 3x e to the negative x squared. Right, just showing it my variable is x. Well, this is improper integrals, right? So this is coming from section 6.6. We know the way that I work with improper integrals. This is the limit as, let's call it b because it's my upper limit, goes to infinity of 1 up to b of this same integral. So now you'll notice I have a regular integral to take, and then at the end of the day I'm going to take the limit as b goes to infinity. Okay. Of course, I could pull that constant out front. Maybe I'll go ahead and do that right here. If I'm wanting to take this integral, you can look at it for just a little bit. Hopefully it won't take you very long to realize that this is a basic u substitution. So I'm going to do the u substitution on this part, just the integral. I have my inside function, which is negative x squared. This would make the derivative of that inside function negative 2x, and I indicate that my variable on that side was x. If I'm looking to make a substitution, I see x dx. I don't see negative 2x dx, so I want to get rid of this negative 2 on this side by dividing both sides by negative 2. So I have negative 1/2 du is equal to x dx. So this integral is the integral of x dx is my negative 1/2 du. Here I have e to the negative x squared was our u. So what I'm looking at, I have that constant of negative 1/2. Antiderivative of e to the u is just e to the u. I want to go back to my original variable, so what I have is negative 1/2 e to the u was negative x squared, and the limits for x were from 1 up to b. So what I have at this point is the limit as b goes to infinity of 3 times this piece that we just found. So negative 1/2 e to the negative x squared, and I still have to plug in my lower and upper limits. What I'm looking at is the limit as b goes to infinity of, well, notice here when I plug in that upper limit of b, I would have negative 3/2 e to the negative b squared minus, plugging in the lower limit, I would have negative 3/2 e to the negative 1 squared. And just to emphasize, the x is being squared, so here b is being squared, and here the 1 I plugged in is being squared. Obviously, the negative and negative there will be a positive. If I want to talk about the limit as b goes to infinity in this first piece, notice I have a negative 3/2. What happens to the function e if I plug in an infinity? Well, I have infinity squared, so something large squared is still large, but it has a negative out front. So if you think about your graph of e to the x, it looks something like this. What's happening as you head out towards negative infinity? Well, you'll notice that function is approaching 0. So the limit of this piece is just 0. Notice I still have this 3/2 e to the negative 1 squared is just 1. Right. If you wanted to write this a little bit differently, this is of course 3 over 2, bumping it to the denominator, e. I took the integral from 1 to infinity of my function, and I've got out 3 divided by 2e. So that integral converged to this. Now, does the integral test say that my series converges to 3 divided by 2e? The answer is actually no. What the integral test tells me is because the integral converged, then the series, and I'll write it, that sum n is going from 1 up to infinity of 3n e to the negative n squared, also converges. It does not tell you what it converges to. Right, so just remember this was by the integral test. So we're going to work with a very few specific series coming up. And they're really, again, nice, quick, easy series to work with, so it's well worth knowing about them and knowing these few facts about them. So the type of series we're going to talk about next is called the p-series. And if you have a summation going from 1 up to infinity of something of the form 1 over n to some power, that is a p-series, 1 over n to some power. Well, it is convergent if that power is greater than 1. It's divergent if that power is less than or equal to 1. And just note, if p equals 1, you would be looking at the sum going from 1 up to infinity. 1 over n to the first, that is the harmonic series, which we know diverges, so this agrees with it, it diverges. You can actually use the integral test we just learned before this to show these things. Let's use these facts in a few quick examples. So determine whether each of the following series is convergent or divergent. The first one, I have a sum going from 1 to infinity of 1 divided by the cube root of n. So the first thing I would notice is that I can take this series from 1 to infinity and write it as 1 over n to some power. The cube root I know can be written as the 1/3 power. So the power I have is 1/3. I want to compare that to 1. Notice it's less than 1, so this series diverges. And you can just say it's a p-series. Right, diverges. In part B, I now have a sum going from 1 up to infinity of 1 over n to the 4th. It's very easy to see that this is a p-series. It is 1 over n to some power, and that power is 4. I compare that to 1. You notice it's greater than 1, so I know that this series converges. Right, and again, you can mention it is a p-series. Okay. Very quick and easy to use. The downside is it does not tell you what the series converged to, just did it converge or diverge. It's good to know about these really easy series because I'm going to start using some comparison tests. So if I have something that's really complicated, I can compare it to one of these easier series that I already know about and get to say things about the more complicated series. So the next type of test I'm going to talk about is called the direct comparison test. And what it says, if you have two sequences and they're both positive, meaning they're greater than or equal to 0, so they could be non-negative. How about that? So they're non-negative series or sequences, and one is greater than or equal to the other. So you have two positive or non-negative sequences, and one is larger than the other. Then, if you can show that the series based on the larger sequence converges, then you get for free that the series of the smaller sequence also converges. If you can show that the series of the smaller sequence diverges, then you get that the series of the larger sequence also diverges. Right? And these ideas actually follow the ones we saw for the comparison theorems dealing with integrals. All right. Let's look at an example. Determine whether the following series is convergent or divergent. So here I have a sum. It's going from 1 up to infinity of 1 over n minus 3. So I just want to know, does it converge or diverge? Well, it should resemble something that we know a lot about. Now, this is not the harmonic series, but you should notice that if I look at this inside sequence, so if I want to compare 1 over n minus 3 to something similar, well, it should compare nicely to 1 over n. If I'm comparing these sequences, notice the only difference here is in the denominator of the first one, I have subtracted 3. So I made the denominator smaller, meaning I made the fraction as a whole larger. My sequence is greater than a sequence that I know the series diverges. So this is the larger one. This is the one I know about. I know the smaller series AN diverges. So this means the series of the larger sequence BN also diverges. And you could say that is by the direct comparison test. The idea is you have a series that's a little bit more complicated than what we've worked with, so I compare it to something I know about. It is larger than 1 over n. I know the series 1 over n is the harmonic series which diverges, so I get that the series of the larger sequence also diverges. Part B. I now have a series series going from 1 up to infinity of 1 over n squared plus 3. Again, I want to know, does this series converge or diverge? And I'm looking at the sequence inside. So I'm considering the sequence, and I want to compare it to something. So you may be guessing what I'm going to compare it to. I notice the sequence 1 over n squared plus 3 can be related to the sequence 1 over n squared. Now I've added 3 to the denominator, so if the denominator has become larger, the fraction as a whole is smaller. So I have a sequence that is smaller than 1 over n squared. I know that the series 1 over n squared is a p-series with a p of 2, which is greater than 1, so that series converges. My sequence is smaller than a sequence whose series converges, so by the direct comparison test, the series of 1 over n squared plus 3 also converges. The next test is similar in the way that we want to compare series I'm asked about with series I know about, but it's slightly different. It's called the limit comparison test. So what it says, for two positive series, so a series of AN and a series of BN, if you know or can show that the limit as n goes to infinity of the sequences, AN divided by BN equals some constant where it is not 0 and it is finite. So if I look at the limit of the two sequences and I can show it is a finite value that's not 0 and it is greater than 0, then both series either converge or both diverge. So the short way of saying that, they both do the same thing. So just to emphasize, it's worded a little bit strange. C is a constant that is strictly between 0 and infinity. So it's a positive constant. It is not 0, right, and it is not infinity. We usually take AN to be the series that I'm asked about, and we typically take BN to be the one I know about. It's just a good way of doing it so we can be a little bit standardized. Here's our example. I want to determine whether the following series is convergent or divergent. So here I have a sum going from 1 to infinity of n squared plus 6n minus 5. It's being divided by n to the 4th plus 2n plus 7. And if you were trying to do a direct comparison test, because we learned that one first, you would realize that when you're adding values and subtracting them in the numerator, and if you were doing that in the denominator, it can be a little bit difficult to directly compare it and say, well, this inside sequence is less than or greater than something I know about. So if you're having a difficult time showing that it is less than something or greater than something, that's a good time to use the limit comparison test. If I have a ratio of polynomials, then it's always good to know that this large series, the series of this whole piece, it is approximately equal to the series from 1 to infinity of those leading terms. So in the numerator, the leading term is n squared, and the denominator, the leading term is n to the 4th. We can simplify this to summation going from 1 to infinity. Notice this would be 1 over n squared. Now I'm not saying they're equal, I'm saying there's a relationship there. Now, what's nice is I know about the summation of 1 over n squared. This is the series, a p-series with a p of 2, which is greater than 1. So we know that this series converges. Because this is the one I know about, this is what I'm calling my series of BN. The limit comparison test says I want to look at the limit as n goes to infinity of AN over BN. AN is the sequence inside the series I was given, so it's this n squared plus 6n minus 5 divided by n to the 4th plus 2n plus 7. I want to take that and I want to divide it by bn, the sequence inside this series, which was 1 over n squared, and I want to look at the limit as n goes to infinity of this whole thing. Notice I have a fraction inside of a fraction, so this is the same as the limit as n goes to infinity of n squared plus 6n minus 5 divided by n to the fourth plus 2n plus 7 times, flipping the bottom fraction, n squared over 1. I'm of course going to distribute that n squared to each piece. So what I'm looking at is the limit as n goes to infinity. Here I would have n to the fourth plus 6n cubed minus 5n squared when I distribute through, being divided by n to the fourth plus 2n plus 7. Now I'm taking the limit of just a sequence like we did back in 8.1. So again, you know our trick is that I'm going to take every single term and divide it by n to the fourth. When I do that, I'm going to have n to the fourth over n to the fourth plus 6n cubed over n to the fourth minus 5n squared over n to the fourth divided by n to the fourth over n to the fourth plus 2n over n to the fourth plus 7 over n to the fourth. Hopefully you've gotten comfortable enough with these that you're not having to write out each of these steps now. You should notice that what I'm looking at when I'm talking about the limit of this, well, here I just have 1. Let me write it. Plus, here I would have 6 over n minus 5 over n squared divided by, again, another 1 plus 2 over n cubed plus 7 over n to the fourth. As n goes to infinity, each of these fractions is going to 0, meaning your limit is 1 over 1. Now, what do I care about this 1? This 1 is the c in our limit comparison test, and I need to make sure it is greater than 0, and it is finite. It is, so what that tells me, I would say by the limit comparison test, the two series do the same thing. What is that same thing? Well, the series of bn converged, so the series of an also converges.